Yesterday, after I finished up with work, I went for a walk with my family, which is pretty standard. We're getting to some nice weather out here in Arizona, and we do this thing called the duck route, where it's about a mile walk. We go by this little pond. There's ducks, that kind of thing. Anyway, on the way with that route, we come to this big grass field, and there's trees and everything like that, where we sit down in the shade, and the kids throw a ball back and forth or whatever. But this grass field actually has this big long slope down into a wash for if there's rain, as if that ever happens here. But if there's rain, it goes out, and this is where the duck pond is, with all the little ducks quack over there. So I'm standing up here with my kids, and just was telling, I was like, when I was a kid, I went to a school where they had a big grass field like this, and they had this same kind of slope. And I said during recess, we would actually lay down, kind of like sausages, and roll down the hill. And at this moment, these are the things that Jeremy does that he doesn't quite understand until later. I don't know what hit me. I'm like kind of like this. And so I lay down, and I didn't remember obviously how I did it when I was a kid, but I was like a board. I put my hands by my side and just rolled down this hill. And the whole way down, as I'm rolling, I'm smashing my face on the ground. I'm like and my wife is just cracking up at the top of the hill. My kids are like, "Daddy, are you okay?" So I end up at the bottom. I'm like, that hurt so much more than I remember. And she goes, "You probably crossed your hands across your chest or something." I'm like, "Oh, that's right. That's exactly what it was." And it's funny, I'm looking at the mirror right now. I still have scratches all over my face. But my kids and my wife thought it was a blast. But that's kind of what I think about with IPv6. It's not something you do every day today. Now, someday, I'll be teaching, and I'll be like, "Oh, yeah, standard issue IPv6. There used to be a protocol called IPv4. But it's just, when I come to IPv6, I'm like, it's been so long since I've done this config. I need a little refresher. I need a little review. Cross your hands across your chest so you don't smash your face on the ground. That's what I want to do. I don't want to go into the depth of ICND1 with addressing and how that all works, but I do want to give you a flyby review before we get to really the ICND2 specific content, which is how do you troubleshoot, how do you solve IPv6 basic problems. So welcome to the flyby review. IPv6, kinds of communication: unicast, multicast, and anycast. Gone are the days of broadcast. However, multicast it's essentially the same thing. You send one message to many. It could be many on the same network, which would effectively replace a broadcast. Or it could be one to many even outside of the same network. And you can start transcending beyond and reach multiple networks and multiple hosts on multiple networks with one network. Unicast, what it always was. Anycast is the completely new one. One to closest. And this allows you to have essentially multiple servers in your environment or even on the internet that have the same IPv6 address, and your device will be able to use that anycast address to find the closest server to them and probably get a better response time. Now, when it comes to addressing, you have three kinds of addresses. And I'll say really two. These kind. This one just keeps getting debated back and forth. What these are, link local is used on the local subnet. So for instance, if you have a router and a WAN link across to the other side, they will have actually multiple addresses assigned to them. Every single device should have, most likely will have, a global scope address, which is something that works on the internet. But it will also have a link local scope. As a matter of fact, let me just bring up a command prompt right here on my workstation, ipconfig. And right here, I've got this guy kind of pre-configured. You can see he's got an IPv4 address of this, and a default gateway of this. But then we look at the IPv6 address. Now, this was one I manually typed in just so I could demonstrate a few things as we move forward. But that's my IPv6 address. Right below that, you can see the link local IPv6 address. I didn't do that. The computer or the router will just kind of make that up. It always starts with FE80 and then uses kind of a combination of the MAC address and some other characters to generate it. Now I also want to make sure I mention this is a Windows thing. Microsoft decided to put a little %11. It's kind of an interface identifier after it. That is not part of the address, but boy, does it cause a lot of confusion because people are like, "Man, I thought I got IPv6, and then they threw this %11." It's nothing. Same thing down here. Just anything with a % in Windows, just imagine as if it's not there. So link local addresses can be used in things like routing protocols. They'll establish neighbor relationships communicating directly on that link local, that layer 2 domain address. And they don't have to use their global or their public IP address to do that. And that's really what this global scope address is an internet address. We're going to have to get used to the new world, IPv6, where everything has a public IP address that can communicate directly onto the internet without NAT getting involved. And that's a shift for most people in terms of security, because they're like, I'm used to this NAT boundary where I've got this router and NAT separates the private and the public between each other, and nobody's getting to the private side unless they're invited by a device on the inside, and that NAT translation is a type of security. Well, it's not too far of a stretch to say, okay, well, if there is no NAT and everything has a public IP address, can't you just configure your firewall rules in the same way to say, okay, well, just allow these guys out directly to the internet and just don't allow stuff back in unless it was explicitly requested on the inside. They call that a stateful firewall. That gives you that functionality. It's not too hard to do that and to make that stretch. So we can eliminate NAT completely out of the picture. Now, this one right here is the one that causes all of the debates. It comes in and out of the RFC standard. Essentially, the site local or unique local scope address is the replacement for private IP addresses. We're used to having the 10 dot and the 192.168 and 172.16, all these different addresses that are private in the IPv4 world. And people are like, well, what do you mean there's no private address? So they keep creating and adding site local, and then they remove it. They're like, well, you don't need them. And so I think in the end of the day, these are going away. We just won't see them. I mean, it's more of like people are comfortable having that there, but once they realize that you've got these two things, they're going to say, well, why would I do that? There's no reason for me to create a site local address and add more complexity to an already more complex protocol. Now some of the specifics. The link local address is assigned automatically as an IPv6 host comes online. And I say it's kind of like the 169.254 addresses of IPv4. Like if a host can't contact a DHCP server, it just makes one of these addresses up. Now, these are all a well-known format because they all begin with FE80. Again, coming back to that command prompt that you saw, these first four digits are going to be this way on every single device. FE80, FE80. That represents a link local address, or an address that can only communicate on the local network, the local switch. It won't go past a router. Now, and then it says, and also it's followed by 54 bits of zeros. That's why in this output you always see the double colon right after the FE80. That's just a whole bunch of zeros after it, filling out the first 64 bits. Now you remember that an IPv6 address is 128-bit addressing. So you have 8 octets of love, 1.1, well actually colon, 1 colon, 1 colon, 1 colon. So you have 8 octets like that. So FE80 literally cuts it right in half. So the first for our FE80, if you were to expand it out, 0, 0, 0, 0, 0, 0, 0, all zeros. And then you have, well, the last 64 bits. Now, the way the standard is written is the last 64 bits are actually the 48-bit MAC address with FFFE squeezed in the middle. So, for example, if you have a MAC address like this on your interface, the way that it expands this out, because that's only a 48-bit address, and it says, well, I've got, this first 64 bits here, and I've got 64 bits of this 128-bit address here. I need to expand it. So right in the middle, they kind of divide this line. They say, okay, 1 or 0019.D1, and then there's our dividing line, FFFE. And you might say, well, why'd they do that? Why did they just split it in the middle? Well, MAC addresses are split in the middle naturally because half of it represents the vendor and half of it represents the NIC, the individual NIC. So this identifies who created the network card, and this is kind of the unique identifier that they give to each network card that they create. So I can say, oh, well, that's a 3Com or an Intel or a Broadcom or whatever kind of network. I know what manufacturer because these are well known. I can look them up. So they said, well, let's take the manufacturer over here, put FFFE in the middle, and then at the end, we'll have the unique host, and that is guaranteed to generate a unique link local address that will never conflict with anything else, because obviously there's no MAC addresses, or there shouldn't be, that are the same in the world. Now, Microsoft, being who they are, insist on just making it more difficult for people in the world, and they by default don't follow that standard. Okay, yes, they use FE80 and then all the zeros, but then they're just like, let's go random, woohoo! Let's just make up whatever else is going to be this MAC address and jam a bunch of characters in there. Now, if you Google online, Microsoft is insane, or a little more specifically, Windows 7 IPv6 auto assignment. People are like, for some reason, Microsoft decided that they would use a random and not the standard EUI64 way of assigning it. But they say, okay, here's how you fix it. You can actually go to a command prompt, and if you get your Windows gurus on board with you, they can actually do this using group policy, run a little script on all their PCs, so that it will actually turn this randomness off, because Microsoft insists on making it an administrative nightmare, and go back to the standard of EUI 164. Then you'll start seeing your FE80 addresses generated the right way if you have a Windows-based operating system. Let's talk public IP addresses, or more specifically, global addresses. The IANA, the Internet Assigned Number Authority, the people that manage all of this to make sure it doesn't turn to pure chaos, has said, you know what, for the foreseeable future, and I'll say, as long as we are on the planet Earth and don't have something extremely weird where we decide to assign every grain of dirt an IP address, we will have the high-level 3 bits set to 001 in all the global addresses that we use today. So, from a hexadecimal perspective, that means we're primarily going to see 2 as the far left number of our global addresses, although this does, with this flexibility, it does allow us to use the number 3 there as well, although I don't see that happening in the short term. So they'll all start with the number, we'll say 2 for now, and then we can break it down from there. Let me go a little practical with you, right? You probably won't see this in an RFC standard. This is just kind of real world how it works. IPv6 addresses are 128 bits, right? Well, you can take those and really break it into 2 different sections, 2 64-bit chunks. The left 64 bits represents the network, if we were kind of talking about it like we did in IPv4, and the right 64 bits represent the host. Now, the host just kind of takes care of itself. With that EUI 64, the host can actually auto-generate their addresses using their MAC address and then jamming that FFFE into the middle of it, and bam, you've got your host identifier. Or if you're Microsoft, you're like, let's just make it up randomly and throw a number out there. So the host ID can just kind of take care of itself. Yes, you can use DHCP version 6, and I'm sure a lot of people will to assign those addresses if you really want to, but why? If the computers can do it by themselves, why not just let them do that? Where our focus is over here on the network side. I think the best way to see this would be to put it into a scenario. Let's just say I, Jeremy, am the network admin of CBT Nuggets. And CBT Nuggets comes to me and says, Jeremy, we want to roll down the hill with you. Let's take us to IPv6. We want to run IPv6 for all our devices in our organization. I would say, okay. I'm going to go to our ISP. Let's just call them ISP1. For now, and I would say, ISP, I want to go to IPv6. Give me a block of addresses. Poof. It's kind of like, wow, where did that just generates a whole slew of questions right there. That first question is, well, how did ISP1 get their block of addresses? Well, they probably went to their local registry, for their country, which in America is ARIN, American Registry of Internet Numbers, ARIN is the company that they would go to, and ISP1 would get most likely like a /32 subnet. So they would, ARIN might say, okay, ISP1, we're going to give you 2001 colon, let's just say 1151, right? Because each one of these in IPv6 address is 16 bits of information. So this right here would be a 32-bit prefix, or 32-bit global prefix of an address. So now that ISP is free to subnet the remaining 32 bits right here for all of their customers. So if they would probably say, well, what are you looking to do? Are you looking to just kind of kick the tires on this, or what are you like? I'm like, well, let's just kick the tires. And they'll say, okay, we'll give you a /64, where they would say, okay, well, how about we give you 1111 colon 1111 /64, which means they effectively give me one subnet that I can use. I get to generate the interface IDs for the remaining 64 bits for my host, but if I want to have more than one VLAN or something in my company, I'm kind of kind of stuck. So what I might say was, well, I want a little more flexibility than a /64. Okay, well, for $59.99 a month, I don't know how they're going to charge for this. It's probably different, but they'll say we'll give you a 2001 colon 1151. Again, that's their global prefix that's assigned to them. Colon 1111 colon 11/56, which now gives me 2 hexadecimal characters right here, or 8 bits of subnetting love, where I can go change these numbers and create all the different subnets in my organization. And I would say for most people, unless you're doing something really weird, where you got a lot of stuff, that's going to be more than enough addresses that they're able to use with a /56 prefix. And the ISP1 now has more than enough characters from there. So then I can just start adjusting my subnet mask and create all these individual VLANs inside of my company where I assign these 2001, 1151, 1111 addresses to, and create individual subnets for that. So that's how you kind of play around with this global prefix and the subnet ID. Okay, just as I was talking, I was like, let me talk about the great debate that is raging right now in the IPv6 world. Okay, if you've ever done the public IP address thing before from an organization, or for an organization, even in IPv4, I'm not even talking going IPv6 yet, it's a pain to change service providers, right? Like, let's just say this is IPv4, right? Then if you got like a block of IPv4 addresses from the service provider, you would put those in as NAT entries, you would assign those to your servers inside, or whatever. But if you ever reach the point where you're like, you know what, ISP1, you are charging me way too much money, I am changing ISPs to ISP2, well, they're going to take their addresses back, right? Because that's their public addresses that belong to them, that were allocated to them. Okay, you see where I'm going here. Let's move ahead to IPv6, right? IPv6, they give you addresses that are not only used for your servers, but are used for everything, every printer, every coffee machine, because I'm sure they're going to be IP enabled, every camera, every computer, every server, everything in your organization is given to you by this IPv6 block from the ISP. And all of a sudden they go, hey, guess what? Time for rate increases, cha-ching, and they increase their rates by double. What do you do? I mean, you're kind of like, okay, I don't want to stay with you anymore, but the amount of pain it's going to take me. I mean, talking CBT Nuggets, I mean, is I don't even know. CBT Nuggets keeps growing. They have a lot of people now. I would just say, I mean, if you're a 10-person company, it's painful enough. But if you're a 1,000 or 10,000 staff, it's just like, I'm stuck with this ISP forever because there's no way I can go through the administrative pain of changing every single address in my organization. So right now there's a big rally. You might say, well, okay, can't you get it's called PI, Provider Independent Address Space? Well, that's the debate. That's what everybody's talking about right now. Maybe by the time you hear this, it will be solved. But the big problem is, well, if you only need a /56, you can't just go to Aaron and say, well, I want a /32. They're going to be like, well, what's your justification? What are you using it for? Or even if Aaron did allocate you a private address space of /56, there's all kinds of routing issues where they can't just start throwing these all over the place, because then we can't summarize, and the routing table for the internet becomes astronomically large, and a lot of ISPs will start filtering you because your /56 is going to clutter up their routing table. So it's this welcome. This is not going to be on the certification exam, right? Everybody with me? But this is just the debate that's going on right now, is because there's going to be so much pain in changing ISPs because they give you every address that you're going to use. How are we going to do this? How are we going to make this provider independent so you can easily change and not be locked into that ISP, but at the same time not flood our routing table with all these tiny subnets of customers around the world? Let's change directions just a little bit and now get into the IPv6 configuration and troubleshooting of just basic network connectivity. What I've got here, just very, very simple scenario. I've got a router connected to a switch with my PC that I'm recording on right now connected to it. Okay, so I'm going to bring up that router. First, let's do a show IP interface brief because it is enabled for IPv4. It's been the same one we've used for a couple things in this series. I'm going to go in and enable IPv6. So it's IPv6 unicast routing is what turns on essentially the IPv6 routing capabilities. IPv4, it's on by default. It's just IP routing is on every single router that you get from Cisco. So now I want to go into the interface. Let's go into interface fast Ethernet 0/0 and give it an IP address. I'll do IPv6 address. Hit the question mark, and here's our options. I'm going to say, let's do 2001 colon, let's go real simple, 1:1/64. So expanding that out, hang on, let me just keep that window on top. That's, I'm going to have 2001. If we were to put it in reality, it would be 0001 because it drops the leading 0, then 000000/64 is my subnet or my network portion of the address. Then, you know, if I were to go from there, I would do colon 00000000, all these zeros, and then 1 as the last address. So it's actually an address of pretty much all zeros, which I represent by this double colon. That's the way of shortening an address. We talked about that in ICD 1. So I'm going to do IPv6 address. I'm going to add one more thing on there, auto config. What that does is say, okay, use your route advertisement capability to now let all of the PCs and devices on that network know what the subnet prefix is. So now this guy's announcing. We'll do 2001. Let me just do a show IPv6 interface fast Ethernet 0/0. Right there, and you can see we've got these router advertisements being sent every 200 seconds that allows these guys to know what the prefix of this network is. So they're saying, okay, well, that's actually 200 seconds, but I really meant 2001 colon 0001 colon and then /64. So all these guys know what they are. And now the computers will receive that, and then they should auto-generate their address. I'm going to give them some time to do that. Now, by the way, this is my computer right here. All I've got is IPv6 set up for automatic. So hopefully it receives something. We'll find out in just a second if it does. So meanwhile, I also want to add another interface on here just for testing purposes. I'll do interface loopback 0 IPv6 address. Let's add another one. 2001 colon. Let's do 2:1/64. Okay. Do a show IPv6 interface brief. Good grief, I got these messages keep cutting my text in half. All right, so there's my fast Ethernet 0/0. You can see it generated that link local address. So it took its MAC address right there, put FFFE in the middle. That's our true EUI 164. And then it says, I also have the global address of this. Then down here on the loopback, it went ahead and generated the same link local address. You know, it's okay, it's the same. It's a loopback, it's not real, but it's just borrowing the MAC address of fast Ethernet 0/0. And then it says, okay, and here's also my global address for loopback 0. So I'm going to come to my computer right here and clear that off, CLS, and do ipconfig to see what I've got. Sweet. So right here I've got the IP address that Windows generated. Now again, Windows does not follow EUI 64. It just generates a random address, and actually on top of it all, it'll generate a temporary IPv6 address that it will change every single time you reboot this computer. At least the IPv6 one will stay the same even though it's randomly generated. You might say, well, why is Microsoft's going crazy here? Why? Well, Microsoft's main reason for not using EUI 64 is because they don't want users to be identifiable on the internet. So, for example, think of you or me sitting at our house surfing the internet. In the IPv6 world that we're getting into, we will have public IP addresses assigned to all the devices in our house. And if somehow, some way, we end up at a wrong site, wrong location, somebody could start tracking us down to our house because our IP address never changes because we are using the EUI 164. Or sorry, not, why do I keep saying 164? EUI 64 to generate our address, and it's based on our MAC address. So as long as we're using that same computer in the house, we're always going to have the same address. and they can kind of track us down, show up at our door, weird things like that. So Microsoft says we are going to have temporary addresses that will change all the time, that will be used, which I would say for home users is fine, but in a business network, for sometimes servers or devices that we want it to stay the same, that's where we would want to use UI64 or just manually type it in there. So that's where these come from. But you can see that I now have the IPv6 address assigned to this device. So I can do pings. I can say ping. Let's ping the router. 2001:1:1, right? It's coming back, and it's like, bam, I'm right there. 2001:1:, I'm getting there. Ping time 1 millisecond because it's on the same subnet. So now we're starting to get into the troubleshooting. I showed you the base setup of IPv6 on this network, so between a host and a router. Ping I can now do to verify connectivity. The reason I assigned a static address to the loopback interface as well is I wanted to show a traceroute. So let's do a traceroute, TRACRT, and do 2001:2:1. So I'm going to go to, well, I guess not much excitement, because again, this device automatically figures out its default gateway. Now notice it's using the link local address to get to its default gateway, and that's how it figures out who it is. Throws that %11 on there as the interface identifier for that link local address. So it, if it has multiple interfaces, it's able to tell the difference between them. But that now gives me the ability to test and see that I'm going through my default gateway to reach the loopback interface. Now let's say we weren't getting to our default gateway. That's where we can look at verifying our layer 3 to layer 2 mapping. Now in IPv6 there is no ARP process, right? ARP is gone because there is no such thing as a broadcast in IPv6. But I mean, they have an equivalent thing. It just uses ICMP to send a little multicast on the local subnet to find out MAC addresses or whatever layer 2 address it's trying to find. Well, instead of doing a ARP-A on our clients to find out what MAC address to IP address mappings they are, it's not as pretty. We can do a net show, or a net SH, I should say, in the Windows world is used for a lot of stuff. So you can actually set IP addresses. There's a lot you can do with that, but you can type net sh interface. I'm hitting tab to finish it for me. IPv6 show neighbor. It's like ARP-A was a lot easier. This is now the new ARP-A, to where you're able to see, in this case, I see that my router 2001:1:1 actually has the MAC address of this right here. It also maps, you can see the link local address to that same MAC address. So this is our new ARP table, if there is such a thing, in the IPv6 world. Now on the router side, you can do a show IPv6 neighbor, a lot easier than on the Windows side, and see that same information. So I can say, okay, this is my host PC, and it shows the MAC address of my PC right here that's showing up. Again, same kind of information that it can discover on the local subnet. Further verification, we can check out our default gateway, just do an ipconfig. And I don't want to make this sound like, oh man, it's all different. It's still the ipconfig command. You can verify that my default gateway, it actually uses the link local address to reach the router on its default gateway. But I mean, even I can even telnet. Telnet 2001:1:1 get. Well, I actually had a password set on my router. Let me do line VTY04 password Cisco. Come back here, hit the up arrow. I mean, you can telnet via IPv6 address, and it's just a new IP address. All the functionality is still the same. I'm looking at verifying DNS. It says, okay, well, DNS, you can still go in and do an NS lookup. I can say NS lookup and type in. Now, I'm on an IPv4 world, so if I type in cbtnuggets.com, I'll get the IPv4 address. But if it is an IPv6 mapping, it will show the name and then the IPv6 address. You can also go and edit a host file. The host file, this takes me back to my Windows days. When you go to Windows System 32, the things you remember, drivers, etc. Wow. This is where Microsoft puts their host file. So does it have a more command in Windows? Host? Yeah, it does. So I could come in here. Now, this is just showing examples. Actually, here's a mapping I have for my house because I don't use DNS in my house. But you can see that I've mapped this IPv4 address to the name storage. So I can actually access a device, ping storage. even though I don't have DNS, and it resolves to the correct address. Well, we can go in to that host file. I can type in notepad hosts, and I could type in an IPv6 address. I could say 2001:1:1 is really my router. And that's just the name I want to assign to it. So that way I don't have to type these names all the time, because you can tell they're very painful. Now I can come back into ping router, and it automatically fills in the IPv6 address just based on editing that host file. As we're completing this IPv6 general troubleshooting step, the last piece would be to verify access control lists, if you had any applied. Now, access lists in the IPv6 world are, as everything, similar to IPv4, but instead of typing IP access list, we actually type in IPv6 access list. And there is no, by the way, standard access list in IPv6 where you can deny only on the source address or permit only on the source address. Now the only thing we have is extended, so now it just says word. What is the name of this access list? So I would say CBT ACL. And then come in here. Now we're right in there. And same thing as before. Permit. I mean, TCP, UDP, all those things are still the same. It's just our addresses get big. So, maybe I do a permit TCP for any source going to any destination equal to 23. So I'm permitting telnet access using this access list. And then you can go in and apply it to an interface. We'll say interface fast Ethernet 0/0. And we do IPv6. Now they actually got rid of the access group command. Now the command is traffic filter, which actually I think is a much better name than access group. So traffic filter, then your access list name, which we called CBTACL. I believe, right? And then you choose the direction in a route that you want to go. Now, of course, as soon as I do this and apply this, I've now killed all connectivity to my device, because the only thing it's permitting is telnet. So I guess I shouldn't say all connectivity, but for instance, if I were to come here now and hit the up arrow on pinging the router, it's like destination net unreachable, but I should still be able to telnet to the router. Yep, and it's allowed, so I can do a show IPv6 access list. Hit the enter key, and we can see CBTACL right there. We've got telnet, 5 matches. So I'm getting, you see what I mean? So again, same concept as IPv4 access lists. They can definitely disrupt our traffic flow. And there we have it. Just like remembering how to roll down a hill, we have to remember all of the core addressing of IPv6, the link local, the global, how they automatically generate addresses. And that bled into the general network troubleshooting. Again, same concepts as what we had before, just now kind of a new way of thinking about it. Well, I hope this has been informative for you, and I'd like to thank you for viewing.